Okay, I hope everyone's back from their short break. So we've been kind of moving out from solar sources towards radio emission. We just had a nice talk by Richard Harrison, different Richard, about CMEs. And now we're going to kind of move out a little bit further and look at IPS, or Interplanetary Scintillation, if I can speak properly. So we have Richard Fallows, who's a scientist at ASTRON, who's going to speak to us about interplanetary scintillation. And I guess I'll just hand over to you, Richard.
Yep. Okay. Thanks. I'm sat outside in my house in the Netherlands, so you'll have a general background of birds tweeting, perhaps the odd tractor, for which I apologise for the tractor, not for the birds. So enjoy the nice garden sounds in the background, and we'll take it from there. Basically, I've prepared a bit of a talk about IPS to be able to explain a bit about what interplanetary scintillation is all about and the kind of science we're doing with it, particularly with a phenomenal instrument like LOFAR. So I'm afraid I haven't prepared any kind of demo to do with these data. They're not complex in themselves to deal with, but there's a great deal of care needed in analysis of IPS data. So it's not necessarily something for people to dive straight into without some expert assistance in the general case. So I'll share my presentation in just a moment. So as we go through, if you have any questions, please feel free to just dive straight in. I'll try and keep the chat box open and see if anything happens on there, but I'm not sure how well that works with sharing the screen. So if you have any questions, you're welcome to put them in the chat, or else just speak up, and there'll be plenty of time to answer those questions and for a bit of discussion if people want as well.
I'll try and keep an eye on the chat box and kind of forward any questions into you as well.
Yeah, that's great. Thanks, man. Okay, so you should be able to see my screen now. Oh. So as Shane said, I'm Richard Fallows. I'm a scientist at ASTRON. I also used to be a support scientist for the LOFAR radio telescope back in the days when we were commissioning the instrument. So I know a fair bit about the instrument itself and the various intriguing and sometimes slightly nefarious ways in which it can be used. So any questions about any devious experiments you may think about wanting to run, you're welcome to also get in touch with me about that. So first of all, then, what is scintillation? What am we actually talking about here? What we're talking about is the rapid variation of the received intensity and phase resulting from scattering of the signal from a compact radio source due to density variations in the intervening medium. So this means that for astronomical radio sources, which I'm primarily concerned with, then the signal can be scattered by an interstellar medium, it can be scattered by the solar wind, or it can be scattered by the ionosphere. And it's the size of the radio source which really determines which of these media can be the cause of any scattering seen. So if you want to observe the interstellar medium, for example, you really need to use something ultra compact, basically a pulsar, and nothing else will do. Whereas if you want to observe the ionosphere, then observe what you like pretty much. Cassiopeia, Cygnus, they're big, powerful, strong radio sources, and they scintillate beautifully due to the ionosphere at LOFAR frequencies. So feel free to use something like that. Conversely, something like Cassiopeia will not scintillate due to the solar wind. So if you're seeing the scintillation on Cassiopeia, it's the ionosphere and not to do with anything else. So for IPS, for interplanetary scintillation, we tend to use basically fairly compact objects like quasars. So much of the 3C list we can take a look at as radio sources for for IPS. So what do we actually see? Well, this is what we actually see with LOFAR, thanks to some ultra-fast imaging and a serious amount of analysis undertaken by David McKenna, now a PhD student at TCD, when he was a summer student with me here at ASTRON a couple of years ago. And what you're looking at is one of the strong quasars, 3C147. It's you can see it's basically increasing and decreasing in brightness quite a bit. You see some slight position shifts as well. Those are probably not real in terms of the interplanetary medium, in terms of the solar wind, but they may well be associated slightly with the ionosphere. But the flickering that you see there, the increase and decrease in the flux of the source itself, that is basically the interplanetary scintillation itself. And this is our ultra-fast imaging, as I say, sub-tenth of a second integrations at 150 megahertz there. If we're taking a look at the ionosphere in a wider field of view, then what you might see is something like the image on the left here. Now, this is the 3C196 field is being imaged by the epoch of reionization group, and these were 30-second integrations some time ago. So we don't see the flickering of the flux density of the radio sources here, but what you do see is the position of the sources moving around. And so that's another effect. That's basically the effect of refraction due, in this case, to the ionosphere. So we've probably got some traveling ionospheric disturbances moving across the field of view. And you can see the difference compared to a quiet night in the right-hand image there as well.
Richard, I have a quick question. Are these observations with the LOFAR core, or the core and remote stations, or a single station, or what?
This particular observation, I think, was the entire Dutch array, probably.
Okay.
The previous observation was only the core stations.
Thank you.
Because for snapshot imaging purposes, we really need as many as much infill of the UV field as possible, basically. Which I guess is something that Pietro's probably already gone into with you guys, but I don't know. So what can we look at with a single station? Well, the single station also can do some more sky imaging, and here we can see both Cassiopeia and Cygnus flickering away. And they're really flickering away. As the movie goes on, you'll also see Cassiopeia move across a little bit. And this is completely due to the ionosphere, and that's received by the Kilpisjärvi atmospheric imaging receiver array, Kyra, which is effectively LOFAR hardware up in the Arctic, up in northern Finland. So you expect things to be quite active in terms of the ionosphere up there. But it illustrates completely the full effects of the combination of refraction, what's happening to the radio source, effectively appearing to move and squish and squash, and the flux density of the source flickering away, which is the intensity scintillation, which I'm now going to be primarily looking at with the rest of the talk here. So the general scenario is that we have radio waves from a compact source scattered by density variations in what we typically assume to be a thin scattering screen. We know that that's not physically the case, but this is an inherent assumption that we tend to make in analyzing our data. So upon emergence from the screen, the wavefront, the scattered wavefront, initially exhibits fluctuations in phase only. And it's only with distance from that scattering screen that those phase variations, the scattered waves, basically start to interfere with one another. And that results in the intensity fluctuations that we then receive on the ground. And that can be the intensity fluctuations from interference between any pair of scattered waves, or any pair of scattered wave interfering with any remaining unscattered component. So that's the basic scenario that we're looking at there. We also tend to describe scintillation and scattering in terms of whether it's weak or strong, and the definition is somewhat arbitrary when just stated as a statement. So we say that basically under weak scattering conditions, then there's a significant unscattered component remaining, and interference is assumed to be primarily between the scattered and the remaining unscattered components. Conversely, as we get into strong scattering, then we can no longer make that assumption. There becomes ultimately very little of the signal which remains unscattered, and interference is effectively between all the scattered waves. So that's what we call then strong scattering. Now I highlight weak scattering because we inherently assume in our analysis that the scattering is weak. So if we think that the scattering is strong, we know that our analysis might not hold completely. So it's good to take a look at a dynamic spectrum like this. Now this is a full dynamic spectrum, again taken by the Kaira instrument up in Finland of ionospheric scintillation, but it shows you exactly the transition between weak scattering and strong scattering, and even in this particular image, some effects probably of refraction at very low frequencies. So we can see that in the weak scattering regime, if we take just simply the bottom panel here, if you were to take any individual frequency here, you would see that the basic pattern of scintillation, the basic pattern of how the intensity fluctuates, that remains coherent across that band. You could take 240 megahertz, compare it with 210 megahertz, and basically the peaks and troughs of flux intensity would be occurring at pretty much the same time. As we get into the middle panel, you can see that that starts to no longer hold true. And what you start to look at is effectively what appears to be an interference pattern in the dynamic spectrum. These in peak intensities and peaks and troughs of intensity, they effectively start to interfere with one another. And then that interference is very, very evident in the lower panel here, where we're most definitely into strong scatter. So with IPS, we tend to want to be at these higher frequencies here, at these in this kind of a range where the peaks and trough of intensity generally remain coherent across the band. So we'll move on now to take a look at the basic observables that we have with IPS. So let's keep things fairly simple for the moment. We have effectively a single station, and effectively that single station is receiving a single frequency. And from that single frequency, we see fluctuations in the received intensity with time. So we have this basic time series going on up here. And this top panel here shows you what the ionospheric scintillation looks like. And then we can take the power spectrum of it and ultimately start to analyze the power spectrum to tell us a bit about the medium that's causing the scattering, how fast it's moving, a bit about the density structure of it as well. And you can see the equivalent power spectrum here. In the lower panel, which is a shorter duration observation, you can see the interplanetary scintillation. And we can see in the interplanetary scintillation case, the IPS case, that the typical time scale is much, much shorter than that of the typical time scale for the ionosphere. And you end up with a power spectrum given on the right panel here. Now, these power spectra are deliberately offset in the display here. So effectively, this 10 to the -1 spectral hertz here is matching up here. So you can see that with the IPS case, we have a fairly obvious shape to the spectrum. This flat section, this knee, and this power law decline, and then we get to the noise floor at the bottom. and the blue spectrum superposed on it is a filtered spectrum. So we've subtracted the noise floor from it and applied low and high pass filters, which I'll detail a bit later on. So if we were worried about confusion between IPS and the ionosphere, well, we can see that for the most part, whilst it is possible, whilst there are circumstances under which they could be confused, for the most part, what's happening in the ionosphere is happening in terms of the IPS spectrum deep in here. So we can filter it out quite easily. We know it's there. And the rest of the spectrum, which is what we're actually interested in and what we actually want to ultimately try and fit perhaps, that remains mostly broadly intact. The other observable that we can come up with is basically to take a look at the amount of scintillation that we see. Just how strong is actually the scintillation? And that can be quantified via something called the scintillation index, which is effectively a measure of the RMS of the received intensity. And that is directly proportional to delta NE, so the variation in the electron density of the medium causing the scintillation. Now we know that delta NE is related to the actual density NE, but the exact relationship depends on solar wind conditions in the line of sight. So it depends on whether the solar wind is slow, fast, or more importantly, whether you got interaction between fast and slow streams, whether there are CMEs in there, etc. So whilst we can say that if we have an enhanced amount of scintillation, we certainly have an enhanced delta NE, and we most likely have, and we certainly have an enhanced density, we can't establish necessarily the direct relation to say that the density is this. We can't yet establish that from IPS. So the scintillation index, therefore, naturally varies with distance from the sun, as you can see from the plot here for one of the radio sources for data taken by the UT telescope in India. And you can see how it broadly varies with distance from the sun. Effectively, there's a very sharp increase close to the sun to a peak, and that increase here is basically the signal being in strong scattering. So we disregard observations taking place in that kind of regime, and we're interested in observations taking place in this regime, which is the weak scattering regime, and we can see how it then generally follows a reasonable decline with distance from the sun. So if we have a large number of measurements taken over a year or so, then we can fit a curve to these, an average curve to these measurements, and say, well, that's a base level of the scintillation for any given distance from the sun. And we can see how much the scintillation is actually increased or decreased above that line. And then that is something which we call the G level. And this G level is something that we tend to plot as being the measure of the amount of scintillation that we see. And it's that we quote as being related to the density of the solar wind itself in the line of sight. Okay, so getting into a little bit more detail now on how we go about analyzing these data. So we've got the nice pretty image on the pretty movie, thanks to David, on the left there. That's resulted in the a time series here. Again, this is just taking a frequency or averaging across the frequency bands to get a single time series. We've taken the power spectrum of it, and the raw power spectrum is the black dotted line there. So you can see that inside here, where it's where we expect it to be generally flat, there's a bit of an enhancement. And that enhancement can be ionospheric scintillation, as indicated earlier. It could also be some kind of other slow system variation. Either way, we don't want it, so we filter it out. So we apply here a high pass filter to exclude this. Now here I tend to emphasize this to my fellow colleagues in the IPS community quite regularly. We need to be careful with where we apply this high pass filter, because just occasionally there is valid signal that we want inside of this point. Now, an example that I give, and I haven't got a display of it, is from last year. If you remember, there was this fabulous comet gracing our skies, a comet Neowise, which we could observe pretty much this time last year. And almost exactly a year ago, I observed it. I observed the source 3C196 passing behind the tail of the comet, very close to the comet itself. And we expect then and the comet tail, despite being about 100,000 kilometers wide in a line of sight extending for 2 or 3 astronomical units, it still provided a serious enhancement in the amount of scintillation that I saw. And we were expecting then the tail material itself to be traveling slower than the surrounding solar wind. The surrounding solar wind was going at 700 kilometers per second, and we were expecting the comet material to be around about 100 kilometers per second. But when I was performing my analysis, I could see that there was some significant noisy variation going on with terms of the speeds that I measured within the comet tail, but I couldn't say that it was definitely at 100 kilometers per second until I took a look at the power spectra and realized that for the duration of the radio source being behind the comet tail, there was an enhancement here inside where I put the high pass filter. And that enhancement was not there beforehand or afterwards. So it was a pure enhancement due to the comet tail itself. And I had to remove the filter. And when I moved the filter, bingo, we got the comet material traveling at 100 kilometers per second. So we need to be pretty careful with where we apply this high pass filter. Now, then there's this slight flat section. We've got this knee here, which we call the Fresnel knee, and that's related to the velocity of the material crossing the line of sight. And there's a power law decline here, which tells us something about the structure of the density structure of the intervening medium. And then we've got a noise floor here, which is the white noise of the system. So we subtract that from the spectrum and apply a filter, a low pass filter at that point as well. So the spectrum we end up analyzing is the one given in blue here. And now for the scary mathematics part. It's not that scary. Don't worry about it that much. It's merely the standard weak scattering formula, which people like me tend to look at and think, oh, geez, this one again. And people like you probably look at it and think, what the hell is that rubbish? Okay, so the very start of it here is that we assume that scattering is coming from a thin screen as usual. And that screen has a velocity perpendicular to the line of sight, VP here. And then the power spectrum is described by this formula, which includes the all-important parameter V, the velocity, but it also includes the spatial spectrum of the intensity scintillation itself. And that spatial spectrum is given by this formula here, and that contains a number of parts. There's a load of constants, which we don't care about for this purposes. There's this F component here, which is both a combination of the Fresnel filter, which is basically what's leading to the Fresnel knee. Effectively, this filter is filtering out scattered signals which are too close to where we are. And that's what leads to this flat section of the power spectrum before we reach this knee. That's all to do with the Fresnel filter. There's a source visibility function, which I'm not going to discuss at this point. So that's in there as well. And then there's this phi NE. Now that's the spatial spectrum of density variations. So effectively, this is describing the scattering screen itself. And we always assume that the density variations are effectively elongated in shape, probably elongated in the direction of the magnetic field. So they have an axial ratio AR. There's a spectrum of them. So that spectrum has a power law exponent alpha. And then there are various turbulent scales associated with it, in particular the inner scale, but I'm not going to go into any detail about that. So that's all this formula is. These are the kinds of parameters that we can extract if we have enough information in our observations. Now, of course, scattering doesn't come from only a single point in the line of sight. It comes from an extended medium covering much of the line of sight. Now there is for IPS a 1 over r to the power 4 dependence of the scattering. Now that means that effectively we can commonly assume that the vast majority of the scattering is coming from the point of closest approach of the line of sight to the sun. So that's great. We can assume we can assume that, and we can assume that it's mostly coming from there and not from anywhere else. But we can't completely discount everywhere else in the line of sight. If, for example, most of the line of sight is immersed in the fast solar wind, less dense fast solar wind, but the tail of the line of sight is immersed in a slow solar wind, which is much denser, then that slow solar wind is still apparent in our data. So we need to be aware of it. Similarly, if there's a CME somewhere in there, that may well dominate things, whether it's crossing the point of closest approach or not. So we use a simple approximation called the Born approximation, which basically sums up the scattering from a number of thin screens along the line of sight. So we say, okay, at particular positions along the line of sight, we've got a thin screen which has these parameters to do with the solar wind. That results in this power spectrum. We take it along to the next one. We simply do the same again, but we treated it effectively as an independent screen, and then just sum up all the contributions along the line of sight, and we end up with our result. And generally, under the weak scattering regime, this works pretty well. But obviously, we need to know where stuff is in our line of sight and something about its properties. So we either need to find that from our observation, or we need to find it out from supporting data.
Richard, can I interrupt for a very quick question?
Absolutely.
Can this approach be applied to ionospheric scattering? In other words, can you just keep adding screens for the different effects?
Yes, it can be. The ionosphere is sort of is a bit more complex because it's a much more obviously thick medium, and a very complex thick medium. But in general, actually, we can apply this kind of approach. The question is the number of screens and where they are. So I wrote a paper last year, I think it was last year, about an observation in which it was fairly obvious that there was scattering coming from two different layers in the ionosphere. I'm not going to go into detail here about how we knew that, but we did. And we could say, okay, these are clearly traveling at two different places. Actually, no, to answer this question, I will need to go into it. Take a dynamic spectrum of intensity. So we got a nice dynamic spectrum of the intensity. Now take the two-dimensional FFT of it. So you end up then with what's something called the delayed Doppler spectrum. And the delayed Doppler spectrum is effectively then a sort of a forward scatter version of a radar spectrum. So under some circumstances, for pulse observations, they've been doing this for years. But under some circumstances in the ionosphere, what you see in the delayed Doppler spectrum is an arc, very nice, simple arc type structure. And that arc can be modeled to, and that arc indicates two things. It indicates the speed of the screen traversing the line of sight, but it also gives an indication of the altitude of it, where it is in our line of sight. And on this particular observation, there were two arcs. One was very, very steady, it's very stable. The other was highly variable, much steeper, highly variable in terms of its curvature. So we could say from two arcs that we're most definitely got scattering from two different screens, possibly traveling at different speeds. And analysis showed that indeed that was the case. We had scattering coming from the D region and we have scattering coming from the F region of the ionosphere. Now, when I take a look at Cairo data, there are much more complex cases where you've really got multiple closely spaced arcs. So yes, to answer your question, we can apply this approach to the ionosphere, but we need to be careful with the number of screens we need to use and how fast they're moving.
Thank you.
Sorry, it's a bit more of a complex answer compared to what you probably expected. Okay, so just to emphasize the formula a little bit more. So the parameters that we're worried about: velocity of the medium crossing the line of sight, the velocity of the solar wind, effectively in our particular case. That's related to the location, the spectral location of that Fresnel-Ni that I pointed out to you. We've got the axial ratio of the spectrum of the density variations. This is something that can be modeled from the power spectrum, from how flat or otherwise the spectrum is inside of the Fresnel-Ni. Now that's complicated, of course, by the fact that that's where we also apply our high pass filter, and complicated by what else may be going on in there. But in theory, it can be modeled with that. There's alpha, there's power law exponent, which is basically the power law decline of the irregularities themselves. And then there's this one, the source visibility function, which is an elephant of assumed size. And being an elephant and being sat in the room, we're going to ignore it for now. And we've been ignoring it for years as an IPS community, and we really shouldn't. But for the moment, we're going to ignore the elephant. So that's what we can get from simply modeling a power spectrum. But then there's more accurate information that can be obtained by cross-correlation. So if we cross-correlate the intensities received by different pairs of stations. So traditionally in our approach, what we've done is taken an observation using a pair of stations, and we take it at such a time that the baseline between those two stations, when projected onto the plane of the sky, is aligned roughly with the outflow of the solar wind, so roughly radially aligned from the sun. And when we do that, we see that the intensities received by one station are effectively repeated with only some minor evolution a short time later by the other station. So effectively, the pattern has moved from the same pattern has moved across one line of sight and then moved across the second line of sight with perhaps a little bit of evolution in between. So that means that we can use a cross-correlation analysis to get some information on the solar wind itself, and in particular, its speed. So in all of these plots, what you see are two autocorrelation functions, which we don't need to worry about at this point. They act as useful markers for zero time lag. And the black curves are the cross-correlation functions. And you can see that those have a lower peak than the autocorrelation function, of course, because there is some evolution of the structure. And they also occur at a slight time delay. And so the combination of that time delay of that peak compared with the radial component of the baseline between the pair of stations when projected onto the plane of the sky. So that's what I mean by baseline here. That combination allows us to say, well, there's a velocity there in this particular case of this top left plot, 476 kilometers per second. Okay, so this is the kind of thing when we measure with short baselines, we could see a fairly strong single peak, but it may be slightly skewed. And that skew tells us that's possibly there's more than one solar wind stream crossing our line of sight. And so taking the same set of data, but we're using different pairs of stations which have longer baselines, we start to see that, well, okay, well, now there's some bump appearing in the cross-correlation function, which is really telling us that there's a second stream in there. And the peak velocity that we've measured just by simply from the time lag and the baseline, well, that's changed, that's increased to 600 odd kilometers per second. Increasing the baseline to some of the longest we have with LOFAR, up above 1100 kilometers here, then you can see that the cross-correlation function is very definitely separated into two distinct peaks, each of which we can measure. And we can say, well, there's a velocity of the highest peak is about 660 kilometers per second, and of the lower peak, roughly 300 kilometers per second. So basically, we've got both fast and slow sort of wind streams crossing our line of sight. That also means that we need to do careful modeling here. We can't simply take the peak value and its time lag and the baseline and say that is the velocity. We have to do some modeling to get accurate estimates of what this velocity actually is crossing the line of sight. Now, thankfully, LOFAR has many stations covering a whole wide range of baselines in any observation, and this means that we can do a little bit of fitting here. So if I take all the pairs of stations, all the cross-correlation functions, all the peaks, and measure the time lags of all the peaks in all those cross-correlation functions, then and put them on a plot here, then you can see something like the plot on the left. And you can see that there appear to be two distinct lines in there. There's a line going roughly up here, and then there's a line going along at a different gradient. And if we put a breakpoint in and said, well, okay, let's just fit velocities below 400 or 500 kilometers per second, and then let's fit velocities just above 600 kilometers per second, then we measure two distinct speeds here. So one measures the shorter baselines, tends to measure the fast velocity. The longer baselines tend to measure the slow velocity. And for whatever reason, and I haven't quite figured it out yet, this seems to be the case pretty much all the time. If we have more than one stream in our line of sight, then one can be measured with the short baselines, the other can be measured with the long baselines. It's quite handy. I've had no idea yet as to why it is, but it is quite handy. And the other thing is that we can start then to move away from the assumption that the solar wind is moving radially outwards from the sun, and instead say, well, we don't know what direction it's actually moving in, so let's see. So if we just change the change the baseline components to be different off radial angles and perform different fits, then perhaps we get a better alignment of the points at some point. So in this plot on the right-hand side here, for example, you can see that if we assume a radial direction, we've got these scattered blue points. But if we assume 24 degrees off radial, which is not realistic, and I'll go into why that is, but all those points line up beautifully. And then we've got a very decent idea of the stream velocity itself from that. So that means that for the observation which you saw flickering away in the imaging from David McKenna, which is of 3C48s taken back in March 2018, there was some evidence in the data that perhaps there were two fast solar wind streams seen in the data. And when I applied this analysis to those data, indeed, that's what we saw. We got basically fast and faster velocities. So we got a faster velocity, which is more in the which is from part of the line of sight more into the polar coronal hole, and then we've got slower fast velocity from a part of the the extension of the coronal hole to lower latitudes. So we effectively have two fast solar wind streams there, and we could measure their approximate directions as well there from that. We can go further. We can take a look at a CME passing across the line of sight back in September 2017, and we can see in the lower plots in the lower plot here the two velocities quite nicely. So everything's a fairly steady state of about 400 kilometers per second, a steady slow solar wind state. But then the short baseline starts showing this bulging increase up to a peak, and the long baselines show a very sudden sharp increase up to this peak, up to a peak velocity about 900 kilometers per second. Now this was an observation of observation at 82 degrees elongation, so we're beyond Earth orbit. We're looking outside of Earth orbit effectively at an ultra fast CME passing across the line of sight. So you can imagine that this increase that's happening on the blue curve here could well be effectively the pile up of density occurring as that CME is starting to barge its way through the solar wind itself. And then you got the actual main bulk of it passing across at this point, and quite a lot of material following on behind. Part of it also seemed to be picked up when we just simply analyzed the power spectra from different LOFAR stations. Also shows similar kinds of effects, which suggests that maybe different lines of sight are slightly sensitive to different structure crossing as well. So that's an intriguing thingy from it. So this was, as I say, hunting an ultra-fast CME, and we can see the plot on the velocity on the lower plot here, but also show on the upper plot an estimate of the G level. So this parameter that's related, that's the amount of scintillation and related to the density of material crossing the line of sight. And you can see that increases fairly steadily up to an initial first peak, which corresponds roughly with the peak of the velocity. But then there's a much sharper rise in terms of the amount of scintillation that we see about 2 hours later. It's corresponding with a bump in velocity, but not very much more than that. So it's suggesting that there's quite a lot of denser material following on behind the initial nose of this CME. But it's not traveling quite so fast as the nose of the CME itself. So these data are still under analysis, but they're quite intriguing. And just to show you some pretty pictures, we did some MHD modeling of this thanks to Kazumasa Iwai in Japan, and this is modeling of G level itself. So basically, this is an MHD model, but it's displayed in terms of IPS G level. And the diamonds that you see are the raw observations taken by the Stellab instrument in Japan. And also you saw briefly flickering in the top right of the right-hand image, some diamonds which are of the LOFAR data taken. So if I flick back and play that again, you could take a look in this quadrant, and you'll see the LOFAR data flickering away. Assuming it's going to come back. Sometimes the computer slows down a bit when it comes to movies, you know. Here we are. So again, take a look up in the top right-hand quadrant in a bit. So you see this, the CME is coming out now. It's a merged CME front, huge front coming across there, the LOFAR data. And you can see that the LOFAR data were flickering away a little bit ahead of the model CME itself. So that indicates then that either the model is a bit slow in terms of its arrival of the CME front, or, and quite possibly more likely, this is sort of assuming that this is a plane of sky view, that where the CME actually is in our line of sight is not necessarily matched up properly with the MHD data here. Anyway, that's just to show another pretty movie for you guys. We took quite an extended data set from another CME back on the 1st of May 2015. This is almost 15 hours worth of data. There's a slight gap around about 7 UT where the observation fell over, but thankfully I noticed that fairly quickly, and we quickly got it going again. So there's a bit of a data gap there. And the top plot shows velocity, and you can see that there are a couple of gaps there as well. And these gaps are really where the cross correlation functions, for whatever reason, were a bit rubbish. So maybe there's a bit too much interference in the data, or something like that. But the cross correlation functions were really quite rubbish, so we haven't been able to get reliable velocities. But the G level in the lower plot is itself also quite intriguing. There's a general rise in the G level as we go through the day, indicating the arrival of the CME. But you can also see this strange, quite sharply varying wave type structure in it. And I don't know what on earth that is to do with as yet. I really haven't figured it out. It's something that I've only just noticed a few months ago for the first time in these data. But they're another intriguing thing that we've got with a data set like this, which we wouldn't have with only a short snapshot observation. And finally, I'll take a look at the well, not finally yet. We take a look at the full 15 hours in terms of a dynamic spectrum. So this is what we actually receive with LOFAR. So it's a full dynamic spectrum covering 110 to 190 megahertz here, and you can see in this full 15-hour dynamic spectrum that there is these peaks and strange peaks and troughs and structure here, which is quite intriguing. And that's that long duration structure. Though you can see going across here these the wave-like structure that was in the G level plot. And zooming into a 4-minute segment of it, then you can see the structure of the IPS itself. So the structure of the interplanetary scintillation, and you can see that it's not completely coherent across the band. We're looking really a bit into strong scattering here, thanks to this CME passing across the line of sight. Okay, I would suggest that at this point I give you guys a break, if that would be okay with the hosts.
Yeah, of course. Yeah, I mean,
Because we've been speaking for about 50 minutes now, so I'll take any questions you may have up to this point. And if there's any other points you want to discuss, and otherwise, I suggest we take a little bit of a break to give your ears a break, my voice a break, and then I'll carry on. There's not a huge amount more to do, but it's best to take a break at this point.
Perfect. That sounds great. So yeah, if anyone has any questions, please fire away.
I have a question, Richard, just about great so far, by the way, really interesting, but about the baselines. You're saying that do you choose the baseline so that it's in a particular direction? Is that the right understanding I have of it? You're saying that it's or perpendicular to the...
Yeah, I mean that's historic. That's historically what we've done. So back in the days when I was using the ISCAT system up in the north of Scandinavia, then we've only got 3 stations, and we would always try to pick times when a baseline between a pair of those stations would be roughly radially aligned with the sun, if projected onto the plane of the sky. So yeah, we would always typically pick observing times when that would be the case. With the number of stations that we have with LOFAR, and with being able to use this technique to just fit baseline versus time lag for any pair of stations, then we no longer really have to use that, have to make that assumption. We can just make an observation, and then whatever baselines we have, whatever cross correlation functions we have, we could still fit a decent velocity to it.
Okay, cool. Thank you.
Any further questions, folks?
In the plot where you showed what you thought was, I guess, more dense material following the initial CME front, could that be like the prominence material, like the core, the dense core of the CME following along, and the kind of enhancement in front is the CME pileup or the shock?
That would be what I would typically think, but this is 82 degrees elongation. We're looking beyond Earth orbit, and as you see from the MHD modeling, what we're looking at is not a single CME. There's a single CME. There's the one we actually thought we were looking at, the fast one, but that caught up, and you've got a lot of quite. So you got effectively a pile up of the 2 CMEs, which are then themselves barging through the solar wind. So we've no longer got we haven't got a typical CME structure at this point. It's a merged event.